So let's quickly go over what the course requirements are. In this course, you're going to need a laptop or your computing device. You're going to need Visual Studio Code or VS Code, and here are the links to install them for each operating system. So whether it's Windows, Mac, or Linux, if you don't already have VS Code installed. And then you also need a Python interpreter, so you can download it here as well for each operating system. You have Windows, Mac, and Linux. And I would also strongly suggest having a basic understanding of Python and how to program with it, maybe like 1 to 2 months of experience with it at a minimum before continuing on with this course. So without further ado, let's go into the course learning objectives. So the first objective is we want to learn about the theory of steganography for file metadata, images, and audio recordings. The second objective is to learn how to write your own steganography programs for each of these file types individually. And with these individual programs, we will only be hiding a text-based message that you enter in through your command prompt. The third learning objective is put all of them together into one massive steganography program to knock the socks off anyone reviewing your resume. And with this larger program, we are going to actually be hiding more than just a text-based message. We will also be able to hide a file. So you'll be able to provide a separate file, whether it be a PDF or a text file, and actually hide that file inside of these other files, which is really cool, whether it be an image or an audio recording. So the fourth learning objective is not really a learning objective, but more of an outcome. You're going to be the coolest person around because steganography is awesome. You'll be learning a skill that probably less than a percentage of the world population knows. That isn't a proven statistic, but based on how popular steganography is as a practice and how many people know how to program, it's probably very accurate, even though it's not proven. So you'll be learning a skill that really nobody knows. So let's continue. So what is the definition of steganography? Well, steganography is the art or practice of hiding/concealing messages or information within other data, such as file metadata, images, audio recordings, etc. So, it's not the same as cryptography, which is what a lot of people might equate it to. So cryptography uses encryption to hide communications in a way that makes it unreadable to those who don't have the correct key, whereas steganography uses obfuscation to hide the message inside something that doesn't appear to contain a message. So in this course, I'll teach you how to actually alter the color of an image's pixels to hide a message. So it's not the same as putting text inside of an image and hoping that nobody can see it. You're actually embedding a file or a message in the pixel colors, which is crazy. It's super cool. And whereas in cryptography, it's obvious that you are sending a message back and forth because it's encrypted, and somebody who captures that message would need the decryption key in order to actually look at that message, right? So it's security through obfuscation rather than security through encryption. So let's look at the file types used for steganography in this course. For the file metadata, we're going to be using PDFs. For images, it doesn't matter. We'll be using PNGs. And then for audio, we'll be using WAV files. So file metadata. Files have data in them which describe the file. This data about the file is called metadata. So basically, any, say you have a PDF file is going to have metadata describing that PDF file. So files have different types of metadata, and you can edit or add new items to the file's metadata, which will be hidden to anyone who doesn't know to look for it, aka security through obfuscation. In this course, I will show you how to do this with PDF files, and let's check out an example. So here is a very basic PDF file called boringdata.pdf, and it has just some text in here that says, here is some boring customer data. Don't look too close or you might find something fun. And here is the metadata associated with this file. So we can see it has a title of boring data and a producer of SKIA PDF M127 Google Docs renderer. This producer is because I downloaded this PDF from a Google Doc, so I converted it from Google Docs into a PDF, and that's why I get this producer in the metadata. So you as a normal user opening up this PDF, you don't actually see this metadata. You actually have to, go in and access it in a way that most users don't know how to do. So let's look at what happens if we add some new metadata in. So if we look at the metadata now, it's the same file, but I've added in something called Stego. So this is the title of the metadata object. So Stego is the title, and then here's a message that says this is a hidden message. And if you were a normal user and you opened up boringdata.pdf again, you would never know that there is some hidden message inside of the file's metadata. So for the rest of the course, right, we're going to be looking at images and audio recordings. So please continue on to learn how to do those theoretically and actually how to make a program where you can hide these messages and other files inside of these. So in the next course, or in the next lecture, we'll actually be programming this file metadata program. So continue and have fun. In this one, we are going to be installing the Git repository. So what we need to do is, if you haven't installed Git, there should be a article before this video that shows you where to install Git. And then the next thing we'll need to do is I'm going to simply make a directory, and I'm going to call it steg_course_udemy. There we go. And I'm going to change my directory then to steg_course_udemy. And now in that working directory, the next thing I'm going to do is say git clone, and then I'm going to pass it in this URL of https://github.com/ShawneyT159/beginner. Oops. _steganography _course_udemy.git. And it will then clone that repository. And then the next thing I need to do is change my, so we can list it now. So let's type in dir, because I'm on Windows, it's ls to view your file system on Mac. And then let's change the directory into beginner steganography course Udemy, and then let's check out what it has. So we see we have the 1, file metadata, 2, image manipulation, 3, ASCII binary, 4, image steg, 5, audio steg, and 6, the steg program. So these are the directories already complete with what you need to get started. So if we go into the 1, file metadata, and we type in dir, we can see that it starts with boringdata.pdf. So you don't have to go out and find your own PDF. Same thing with image manipulation. This one starts with that image, or with an image in it, and then image steg also has an image in it. Audio steg has a WAV file that you can use in it, and then the steg program has a PDF, an audio file, and an image already in it for you to get started. So thank you for watching this, and as we go through, or as you go through the videos, do just change your directory into the one that we are working on. We are going to be creating a program that will quote-unquote decrypt, right, a PDF file's metadata so that we can view it. So the reason I'm starting with the decryption is so that you can see that the PDF already has metadata attached to it, so we can read that metadata now, so it's not as confusing when we go to encrypt. So I'm starting here with this, blank folder, and this is available on GitHub, which should have been the link to it that you can download should have been available. So all you need to do is clone down this repository using the git clone function, and I'm going to open up a new terminal in my VS Code. So the first thing I want to do is turn this into a virtual environment in Python. So I have Python 3 installed. You might just have to run Python or Python 2, doesn't matter for this function, but I have to run Python 3 -m, and we are going to say venv for virtual environment, and I'm going to name my virtual environment .venv. So this is creating a environment in my folder for Python, which will install all of my imports. So why is this important? Well, say you have two different projects and they require different versions of these imports. Well, then one can't run on your main operating system. So it's good to have a virtual environment for all of your Python projects, and we will have a virtual environment for all of the projects that we're using. So now that we have our virtual environment on Windows, the way to get into it is to type in .venv, so the name of our virtual environment, /scripts, and so yeah, Windows it does these backslashes instead, and then /activate. I pressed tab there as well to autocomplete scripts, and so then we're just going to press enter, and now we're actually in the Python virtual environment. So now from here, the way to run scripts is through Python, but the first thing we want to do is use pip to install a library called pdf2, and what this will allow us to do is access certain features of a PDF file, which we will need to do to read the PDF's metadata. So now we have that installed. I'm going to go ahead and create a file called decrypt.py, and we can begin. So the first thing we want to do is actually import the pydf2 library, and then we're going to give it a path. So let's create a variable called pdf path, and let's make it equal to the path to boring data .pdf. Sorry, PDF. There we go. And now that we have the path of our PDF file in our working directory, we will simply open it using the with open function in Python, and we're going to pass it in the variable PDF path, and we're going to open it up using the read flag and as a binary file. And we're going to open this up as a file. Now, so what does this function do? So we're opening up the boring PDF data, and we're opening it up as read and in binary mode, and we're naming this, we're storing this file as this file variable. So next, we're going to create a reader, and this reader is through the pydf2, and then pdf reader. There we go. And we're going to pass it in file. So now we've created a reader from this pydf2 library, and we passed it in file. So now we're able to read the file. So we're going to create another variable called metadata, and we're going to create that equal to the reader.metadata. And so if we do reader.metadata, this is actually accessing the PDF's metadata. So now we're going to say for key in metadata. So what is this actually returning? Well, this is returning a dictionary with a key value store of the PDF's metadata. So a dictionary sort of looks like this, where you have a key and the key has a value, if you're not familiar with what a dictionary is. And then the way to access this value is we say print. So we're just going to print, and we're going to print the key, right? So this will print out whatever key is. So in our scenario, this is going to be title, and also I don't remember the other one, but so title would be like boring underscore data. So title is the key, and then boring underscore data would be the value. So we're going to print key plus, and we're going to put this in quotes. Actually, you know what a better way to do this is to put an F, and we're going to put it in quotes, and we're going to say here is key. So, and then we're going to space, colon, space, and we're going to give it value. Metadata at key. So now we're looping over every single key in this metadata dictionary, and we are printing the key and the key's value, which is metadata at key. So now if we were to run this, I'm just going to delete this really fast because that's not proper Python syntax. Let's run the script of Python and decrypt.py. And we are going to see this metadata here. So we get title, which is boring _ data, and we get producer, which is SKIA PDF M127 Google Docs renderer. So congratulations, you have officially read the metadata from a PDF file. We are going to actually be creating the encrypt function now for the file metadata steganography. So let's go ahead and let's create a new file called encrypt.py. And I think it's important to first, just like think about what the steps are in order to do this. So let's just do a quick reminder. We're still inside of our virtual environment, right? And to get there was .venv/scripts, /scripts with a capital S, \activate, and then enter, and that's for Windows. And I will have other documentation showing you how to do it for Mac and Linux. And so now let's think about the steps that we need to do. So the first step is we need to import PyPDF2, right, which is how we're going to read and write to the file. The second step is, we need to read the incoming file. So it's going to be boring.pdf is the incoming file. Step 3 is we want to actually create a new file from it. So how do we do that? So we're going to copy the pages from the incoming file to a new file. And so that's going to copy, the page data. And then the fourth step is going to be, copying the metadata to the new file. Actually, we're just going to copy the metadata. And then the fifth step is going to be adding the new metadata object, which is going to be a key and a value, which will store our hidden message to the copied metadata. And then we are going to save the new file. Save new file with the new metadata containing the hidden message. Right, so now that we have our steps, I think we can move forward. So the first thing we're going to do is import PyPDF2, save, and then we're going to give it the PDF path again, which was boring _ data, and let's open it. So with open PDF path, and we want to open it in the read and binary as file, and then we're going to create a reader object like we did last time to copy the PDF. So we're going to say reader equals PDF or Py PDF2. PDF reader, and we're going to pass in file as the parameter. Next, we're going to create a writer, which equals Py PDF2 dot PDF writer down here. And that's going to take no parameters. So next we're going to say, so right now we have read the incoming file, we've created a reader for it and a writer, and the next thing we need to do is copy the pages to the writer. So we need to say writer dot append dot append pages from reader. So then all we need to do is pass in the reader. And so what this function does is it will take in the reader, which contains the file data, and it is going to append the pages from this reader to the writer buffer. And so now let's go ahead and define the message that we want to do. So this is going to be the message. Right, so now that we have the pages copied, right, we're actually going to define our message now, and let's just define the message object. So this is going to be what the key is and what the value is. So we will say the message, or we'll say the key is equal to /key, and the message is equal to this is a hidden message in the metadata. So you might be wondering, why did I start the key with this /? And that's just how PDFs expect the metadata key to start. So every key every metadata key needs to start with this / in order to be accepted. If you tried to append this metadata to the PDF, it would just fail. So next, let's go ahead and let's get the metadata. So next, we're going to copy the metadata. So we're going to say metadata is equal to reader.metadata, right? And so this returns that metadata object, right? Metadata, I'm sorry, not metadata object. Well, it is an object, but a metadata dictionary, which has the key value pairs. And next, we're not even going to like read over or anything. We're just going to say metadata dot update, and we're going to pass in the key message. And now this is going to add the key and the message, right, to the metadata dictionary. So now we're going to say writer dot add metadata, and we are going to pass in the metadata variable. There we go. And now we have officially copied the pages. We have copied the metadata, appended the message to the metadata, and then we wrote that message to the writer buffer. And next, we are going to say with open, and we're going to say this is going to be the name of our output file. So the one with the hidden message, we'll say hidden.pdf is going to be the name of the file, and we're going to say write in binary, as output file. So we're storing this output file we're storing this file with the write in binary mode as this output file variable, and we're going to say writer.write to the output file. And so what this will do now is it's going to take the writer that we defined, which is a PDF writer, and it's going to write all of that data to this output file, which is in binary mode. So now if we were to, and then let's just do a little success message. So we'll say print message hidden successfully. And now let's go ahead and let's say Python tab encrypt.py, and we're going to press enter, and we should see, oh no, no file or directory found. Oops, that's my bad. So this is boring with a capital B underscore data with a capital D dot PDF. And let's save that. And now let's run this again. And we can see the message was hidden successfully. So if we look here, we now have this hidden .pdf. And actually, if we click on it, we can see that it does store this like so. So here is our hidden message. So this is, if you've ever used Linux before and you run a strings command, this is exactly the same thing. It looks for characters in, it looks for characters that can like be turned into a string, and then prints it out to the screen. So, if you're a normal user, you don't know to click on this like this, so it's still hidden. And if you open up the hidden.pdf as an actual PDF file, like the user will never know. So next, we are going to go to our decrypt again. So let's go to decrypt.py. And instead of decrypting boring data.pdf, let's decrypt hidden.pdf. Press save, or Control S for save. And let's do Python and decrypt.py, and it will iterate. Oh, I added one too many Fs. Let's save, and let's run it again. And it'll iterate over our metadata, and we will see here's producer, title, and then here's the key, and here's our hidden message. So congratulations, you now know how to append metadata to a PDF file that average users will not be able to see. We are actually going to be making the full-fledged program to encrypt and decrypt file metadata from a PDF file. So let's go ahead and get a new Python script created. So we're going to call this file underscore metadata underscore program dot py. And so what we want this to do is, one, take in command line inputs and perform that action. So basically, right, what we want this to do is, say somebody runs our program with, let's put this in a comment, Python file underscore metadata program.py. We want it to have like a set of parameters that people can give it in order to do different actions in the script. So we can make it, more user-friendly, and we don't have to write different Python scripts to do different things, and also add in different data. So like some of the parameters we might want are like a -e or a -d. And so the -e and -d can stand for encrypt and decrypt. And we can also say like -f, which is like the file name. We can also have something like -o, which is an output file. So, right, like let's say if you're encrypting, so like if the user gives a -e, then we can say it requires a file name and an output file, so that, the input file name would be boring.data, and the output file name would be hidden.pdf, and the user can define that when running the script. The next thing we will need is like a -mn, which could be the metadata key name. So this would be like the metadata key name. And so like in our previous example, right, if we go back to Encrypt, we had the metadata key name as /key. And so if we go back here, the next thing we're going to need is like a -m, which is the actual message you want to encrypt or like hide in the metadata. So now that we have like everything we want to see from it, let's go ahead and create basically the entry point to our program. So we're going to say if __ name __ equals __ main __, then run the function main. And we're going to go up here and define the function main right here. So if you're not familiar, this is basically defining an entry point to a Python script. So when you run the Python script, right, as it is, it will this will happen, and then it will run the function inside of it. So we're naming it main. You can write other code inside of this as well, it doesn't matter. But for now, what we're going to need is to import something called argparse. So we're going to say import argparse. And what this is going to allow us to do is parse our inputs that the user defines. So like -e, -d, -f, -o, -mn, and -m. So how can we do this? Well, the first thing we're going to do is we're actually going to create a parser. And we're going to say parser equals argparse dot argument parser right here. And we're going to give it a description equal to script that appends user-defined data to a PDF's metadata. Metadata. or reads a PDF's metadata, period. Right, and so, that is exactly what's going to show up when a user runs the help command. So let's say, let's run this really now. So we do Python, and we're going to say, we'll just hit tab until we get to it. File metadata program.py, and we're going to give it a -h. Oh, it doesn't actually work yet. I apologize. Or is it just --help? Oh, whoops. --help. Okay, so it doesn't actually give this when you only define a parser. So now let's do parser. Oh, right, because we need to do args. I apologize. Args as in arguments equals parser dot parse args. And now if we did --help, it will say, yes, here we go. So here's the usage, and then here is the data that we see, that we put as the description. So when somebody does --help on our file, they will see a script that appends user-defined data to a PDF's metadata or reads a PDF's metadata. So, and then it will also describe the usage that we're going to program into it. So now we are going to give it the first argument, which is parser.add_argument. And we're going to say -d. Oops. Oh, no, that was correct. -d for decrypt. And we're going to store it as an action equals store true. And we're going to give it an help equal to option decrypt. There we go. Oops, I spelled decrypt wrong. And now, if we were to run the --help again, we will see -d is to decrypt the file. So, what does -d actually look like? So now, if we were to print now args.d, which is what it'll be stored as, if we were to add the flag, right, we will see, oops, let me get rid of help. We will see false because -d does not exist. Now, if we were to add -d here, right, we would see true. So if we want to determine if the user is trying to decrypt or encrypt, we would just simply say if args.d, then do something, which is going to check if args.d is true, meaning the user wants to decrypt. But for now, let's continue adding in all of our options. So the next one we're going to do is parser.add_argument, and we're going to give it -e for encrypt. We're going to again say action equals store true, and we are going to, oops, I can't see, give it a help option of option encrypt. And we'll just keep going. So parser.add_argument. And the next one we want is -f. And this one is actually going to say required equals true. So when we say required equals true, the script will not run unless the -f flag is given. And because we need the -f flag for everything, we can't, so it can't run without it. So we're going to say it's required true, and then if the user doesn't supply it, then it will say error. We need a -f flag, meaning the file. We're also going to say the type is equal to str, which means the type of -f is a string. So we're going to use that string as the file path. So you could put the file in different directories, so it doesn't actually have to be in this directory. So you can run it and get the file from anywhere, as long as the user describes where the file path is correctly. And then the next one is going to be help equals required. We're going to say actually it's just file path. There we go. And we're going to say parser.add_argument. The next one is going to be -o for the output file. And we're going to say required is equal to false, meaning you don't need this as an output or as a argument. And then we're also going to say the type is equal to string again. And we're going to say help is equal to output file path. There we go. Parser.add_argument. almost done. We need the -mn, comma, required is equal to false. Then the type is a string, and help is going to say, this is the metadata key name. There we go. And parser.add underscore argument -m, which is going to be our message. So required is equal to false, type is equal to str string, and help is equal to the hidden message you want to hide in the PDF's metadata. There we go. Now, so when we say parser.parseArgs, it actually gives us this in a nice format where we can access it using dot notation, as I've shown you before. So this is parsing the arguments given from the user. Now, the next thing we want to do is make sure that all of our arguments are correct. So the first thing we want to check is if, args.d, sorry, one second, if args.d or args.e, then, if not args.d or args.e, then parser.error. The script requires either a -d or -e flag. So this is saying if you don't give either a -d or a -e flag when you're trying to run the script, we're going to error out because we either need to do decryption or encryption, not nothing. So the next thing we need to do and check is if args.d, right, and args.f, then we will run some sort of decrypt args.f. So we'll do some sort of decryption, or what we did before with decryption of the args.f. So now let's just quickly copy and paste our decrypt method in here. So let's go ahead and we'll define decrypt. Decrypt, and we'll give it the file path, right? And we can just go over to our decrypt method here and copy and paste this into here. And let's tab it out. And then let's just change PDF underscore path to, you guessed it, file underscore path. And then we need to import pi PDF2 in order to actually run this. And now we can say tab decrypt args.f. And actually, you know what we should do is instead of saying args.d and args.f, let's say if not args.f, then parser.error. And we're going to say the decryption method requires a file, requires the -f flag with the path to the input file. There we go. And we can say else decrypt args.f. And now if we were to give it this, so let's try to decrypt hidden.pdf now. Let's run Python /file metadata program. Let's say -d -f, and let's actually just add -d and we'll see what happens. We got unknown action. Oh, whoops, I added in, I spelled store wrong. Store underscore true. There we go. Now let's run it again. Required type error required is an individual argument for positionals. Sorry, I might have missed something. Oh, I forgot the dash in front of MN. I do apologize. Let's run it one more time. There we go. Now we get the correct output of file metadata program error. The following arguments are required -f. So, right, oh, we actually took care of that here with required equals true. So we can actually get rid of this and just run decrypt args.f. There we go. And now let's do -f and actually decrypt hidden.pdf. And we can see we get the metadata of /key, and this is a hidden message in the metadata. Awesome. So now that we know that our decrypt function works, right? So let's just comment this and let's say decrypt function. Let's go ahead and create our encrypt function. So let's say def and encrypt. And the things we need for encrypt are the file name, so file path. We also need the metadata name, so metadata key name. We need the message, and we also need the output file path. There we go. And so now what we're going to do is go back to our encrypt function here, and we are going to copy this whole thing, boop, and put it in here. And let's tab this. There you go. And let's get rid of PDF path. And we're going to give this one the file underscore path. We are going to get rid of key and message. And we are going to say, instead of key, we want the metadata key name. And then the message variable is already here for it. And we have writer.add metadata. And then instead of hidden.pdf, we're going to replace that with the output file path. And now we can scroll down here and let's just make sure everything is good. So we are going to say else if args.e, right, if args.o and args.mn and args.m, meaning if args.output file is defined, args.metadata name is described, and args.message is defined, then we can run the encrypt function. So we're going to say encrypt args.f, args.mn, args.m, and args.o for output file. There we go. And then we can say else parser.error. The script requires the it's 0, -mn and -m flags to run the encryption function. There we go. Awesome. And so now if we run this with the -e, and then we give it the -f of boring underscore capital D data .pdf, which is the file path. We also give it the output file path of, I don't know, let's just say output.pdf. We also give it the metadata key name of, oops, I didn't mean to put a comma there. Let's say the key name is steg. And then we're going to give it, we got to put this in quotes, steg, and then we're going to give it the message of, and put this in quotes as well, no one will ever see this, exclamation point. And let's run it. And we can see, aha, incorrect first character in name object steg. So let's go ahead and delete this, because we gave it the incorrect first character. So let's go ahead here and let's go to steg and let's put that / in it. And now everything should be fine. And so our message was hidden successfully. And then if we go to run the decrypt function, So -d, and then we give it the input file of output.pdf, and we press enter. We see here is steg and also the message of no one will ever see this. Awesome. So yeah, we have officially made our first steganography program of hiding messages inside of the metadata of a PDF. Awesome. So like now we will be moving on in the next lectures to images, and then after that we will do audio files. And this will get a little bit more complicated. So if you don't fully understand the lectures first, I do recommend you rewatch them and you try to study the code that we are writing together as much as possible to fully understand and grasp what is occurring when we do least significant bit steganography. What is an image? Well, an image is a two-dimensional array of pixels. This means there are rows and columns of elements named pixels. So if we look here, these are all of the columns, and these are all of the rows. So, like, what characteristics do images have? So images today have height, width, and channels. So height is the number of pixels in each column, that's vertical, and width is the number of pixels in each row, that's horizontal. So, and what are channels? So channels are the number of color components per pixel, and we'll get to that in a second. But just understand that images have three characteristics nowadays, which are height, width, and channels. So image height and width is pretty standard, right? So let's say this picture collage to the right has a height of 120 pixels. Each column is 120 pixels, and the width is 215 pixels. So each row is 215 pixels. So this means that it has 25,800 pixels in total, because height times width is 120 times 215 is 25,800 pixels. So pixels and channels. So a pixel is the smallest element in an image. It represents the color for a specific index in the two-dimensional array, or a grid of pixels. So if you're familiar with arrays, you can do multiple dimensions of arrays. So the image is a two-dimensional array. So a grid basically of pixels. And so let's look over here. So we have grayscale images. So the definition is pixels have one channel where the pixel is a shade of gray represented by an integer between 0 and 255. So 0, I'm actually not sure, but I think 0 is black and 255 is white. So, there's only one channel, meaning it's only got one color value. So in red, green, blue, and you can see here, pixel is equal to one integer value of gray, which is in this example 29. So for red, green, and blue images, which is what RGB stands for, pixels have three channels representing red, green, and blue. Each color is represented by an integer between 0 and 255. So we can see in this pixel example, red is equal to 15, green is equal to 128, and blue is equal to 17, with the higher number meaning a higher intensity of that color. So what is RGBA? So that's red, green, blue, and alpha images. So pixels have four channels that is the same as red, green, blue, but with one extra being alpha. And that represents the transparency in the image. So the transparency of that pixel, meaning you can put pixels in front of that which have a larger or smaller transparency number. So with RGB images, the alpha would just be 255 always, meaning that it's not transparent at all. None of the pixels are. So we can see in this example, a pixel is equal to red of 32, green of 109, and blue of 112, and alpha is 128, which means this pixel would be 50% transparent. So if we continue, so file formats and compression. So let's see here. There's two types of compressions. We have a lossy compression and a lossless compression. So what is a lossy compression? So when saving the file, it reduces the file size by permanently eliminating some data. And that's like an example is a JPEG. And so is this good for image steganography? No, because when we're doing image steganography, we're manipulating the image's data in a specific way where we don't want any of that to change. Otherwise, we could corrupt our message. So using any sort of lossy compression is really bad for us. So we're going to say no, it might accidentally delete pixels or alter them that we have altered ourselves in order to hide our message. So What image formats have a lossless compression algorithm? Well, that's a PNG. So when saving the file, it reduces the file size without losing any data from the image, which is really important for us. So yes, this is good for image steganography. It will never delete pixels that have been altered. We're going to be talking about image manipulation and just getting a feel for how we can work with images in the Python programming language. So I actually have a photo here that I'm going to copy and paste here called example.png, and it's this cute one with, you know, this kitty cat and this dog. And we're going to mess around with this image a little bit using Python. So first things first, let's get everything set up. And again, this is available on GitHub with example.png. So I will, you'll be able to download it from there using the git clone method. So I am simply going to create a virtual environment. So we're going to say Python 3 -m venv and .venv is what I'm going to name mine. So once we get our virtual environment created, then we can start. This can take a second, but so like the Python library we're going to be using is called Pillow, and Pillow allows you to do a lot of things. So you can open an image, you can look at all of its pixels, you can get its size, you can alter the pixels, you can save new images, and do all the things that we need to do for our script to work to manipulate this image. So let's do .venv /scripts/activate so we can get into our virtual environment. And from here, I am going to do pip install and we're going to install Pillow. And it is a relatively large library, so it could take like up to a minute to actually fully install. So for me, did not take very long. So now I'm going to go ahead and create my Python script. So I'm going to start by naming it manipulate.py. And in here, I'm going to say from pill, which is how you import something from the Pillow library. And then we're going to say import image. And I'm going to say image path is equal to example.png. And then I'm going to say image is equal to image.open image_path. And so now we have opened the image library from Pillow is opening up our image from the path we gave it, and it's going to put it into, you know, the data structure that the Pillow library creates. So next we can actually show the image and prove that we've opened it by typing in image.show. And so now if we do Python manipulate.py and we press enter, we will see the image actually pops up. So I have two screens running, so that's why it popped up over on my other screen. So we can see the image will show up here. So now let's actually say, let's get the width and the height of the image. So to do this, we're going to say width, comma, height is equal to image.size. Okay? And then we can actually print the width and the height. And we can see how many pixels there are for horizontally and vertically of this image. So let's do Python manipulate.py, and we can see this image is actually a perfect square with 1080 pixels for the width and the height. So now let's actually see how many pixels there are in total. So let's print width times height, and our image contains 1,166,400 pixels. So that's a lot of pixels. And then if we want to determine how many red, green, blue values it has, so remember each pixel has multiple channels. So we're just going to work with red, green, and blue. So let's actually multiply this by 3 then. And so it has we have 3,499,200 red, green, blue values to work with, which is pretty dang cool. So let's delete this now. We can actually leave the print width, height, and we can leave the print width times height to show how many pixels we're working with. Now let's actually copy this image into a new image, pixel by pixel. So we're going to say new image is equal to image.new, and I want to create this as a red, green, and a blue image, and we're going to give it the width as a set and the height, the set data structure, and we're going to give another set of 0, 0, and 0. So this is saying, create a new image that's red, green, blue with the width and the height of our other image, and set each red, green, blue value to 0 for each of those pixels. So now what we can do is for x in range of the width and for y in range of the height. So we're going to run a double for loop over our image. We're going to say pixel is equal to image.get pixel at the set of x comma y. So don't forget, this takes in a set. It doesn't take in two coordinates. So before we do this, actually, let's see what a pixel actually looks like for our original image. So let's print image.get pixel, and we're gonna say let's get it at the 0, 0 coordinates if it was a graph. So let's print this, and we can see that it actually has 212 for the red, 217 for the green, and 221 for the blue. And we can see that this image actually has 4 channels, so it's an RGBA image, and so it has 255 as the alpha. So that's pretty interesting. So now that we know like what a pixel looks like, right? So we know that if we do the image.getPixel method at coordinates, which are a set data structure, you have to give it a set, it will return a set back to you saying the pixel values, and it'll also, you can determine what the number of channels are, what type of image it is, based on the number of items in the set that it returns. So we can see that this is obviously an RGBA. So I actually just want to create an RBG image, as I've said before, right here. So let's go ahead and copy all of these pixels into it. So the cool thing about Pillow and with this functionality is if we say new underscore image dot put pixel, and right, so we've created an image and it's red, green, blue. Okay. And so when we get this pixel is an RGBA, right? So it has 4 values in its set, but this one is going to be expecting, if we put a pixel in it, it's going to be expecting 3 values in its set. So what happens if we do at x comma y, right? So the coordinates, so we're looping over the width, and then so it's going to be going, right, it'll be going over the width, and then it'll be going over the height. So for each x coordinate, it goes through all the y coordinates, and then it just goes through and does a double for loop. And then we're going to actually give it the value of pixel. So, right, and then what we're going to do is say new underscore image dot show. Something cool happens. Right? Okay, so here's our new image that's being showed, and we can see that it didn't error out. So when you do put pixel, right, if you give it an RGBA, it will only take the red, green, blue out of the RGBA pixel. So you don't have to worry about manipulating this pixel and only giving it the RGBA values. So now, so cool, we copied an image. That's really awesome. Now let's see what happens if we mess with some of the colors. So let's say pixel is equal to, and let's make it a new set, pixel, and let's actually just give it a really high red value. So we'll give 255, and then we'll say pixel at 1 at the first index, and pixel at 2. So we're creating an RGBA pixel, and so if we what this is so basically like pixel at 0, so the 0th index is equal to blue, red. Sorry, pixel at the first index is equal to green, and pixel at the second index is equal to blue, because arrays always start with, and indices always start with 0, not 1, when we're programming. So now we see pixel, and we're going to give it the most amount of red that we can, and then it's going to keep the green and blue values, and then we're going to show the image. So let's go ahead and show this. Let me exit out of this old one, and now the new one comes up, and we can see that it's a super, super red image. So that's pretty cool. Next, we can say new image.rotate, and we can give it -90, and we can see that the image is going to rotate. So new underscore image dot show, and now it will be rotated to -90 degrees. Or not. I may have gotten this incorrect. So angle in degrees counterclockwise. Oh, you know what? I think we need to say new image equals new image dot rotate -90 degrees. And let's run this. And we can see now the image has rotated 90 degrees. And so I just wanted to give this as a lecture to, show what Pillow is capable of more than just doing image steganography, and also just to give you guys like a feel of manipulating images and working with images in the Python programming language. What is ASCII? So ASCII stands for the American Standard Code for Information Interchange, and it is a character encoding standard. But it is not the most popular one, which is UTF-8. That is the most popular character encoding standard. It turns binary into decimal values, which is then turned into readable characters for human viewing and editing. So imagine you have, right, so like each ASCII character is represented by a decimal value or an integer value, either or. Those two are interchangeable in this context. Between 0 and 255. So each integer value is represented by a list of 8 bits, 1s and 0s, also called binary. And if you visit this URL, you can see the complete ASCII table. So imagine you have a string of 8 bits, 1s and 0s, that will actually equate to a character that we can see, such as a capital A, lowercase a, this V, etc. So here's an example of what that looks like. Here we have the capital A character, and that gets turned into, right, by following this left arrow, the integer or decimal value of 65, which actually gets turned into 01000001 in binary. And each one of these binary digits is called a bit. And vice versa. So this binary gets turned into this decimal, which gets turned into this character, and that is how, if your laptop or something is using that character encoding standard, that is how you view that character. And we can continue. So how does binary conversion actually happen? So take a minute to really, take this in, because it can be confusing for a few. So when you're converting binary to a decimal, also known in this case as an integer value, you will simply find the number of the index where 1s are located and add a 2 to the power of the index. You can ignore all 0s. So the index actually starts at the right and then goes to the left. So you read binary right to left. You could read it left to right, but just understand that the index will always start from 0 and go up to whatever the last binary digit is in terms of the index. So because in arrays and programming, our indexes always start with a 0, the first binary digit, if it's a 1, will be 2 to the 0. If it's the next one will be 2 to the 1 if it's a 1. The next one we see is a 0, so for that we simply have a 0. The next one is 2 to the 3 because there's a 1 in the binary digit, right? So if we're following this, we can see the index here, and then here's the power value. So the next one's 2 to the 3, which is 8, and we continue all the way to 2 to the 6, which is 64. Now, in order to turn that into a number, we actually just add up all of the digits together. And so we can see addition, 64 plus 8 plus 2 plus 1 is equal to 75. And so this is the ASCII character of capital K. So it is important to note that not all binary is read in octets, meaning 8 bits. It could be up like 16, 32, etc. So the indices keep going. So if we had 16 bits and we wanted to read them all as one value, we would actually read it 2 to the 0 all the way up to 2 to the 15 power. And you would just add all of the values that are ones together and ignore all the zeros at the indices. And that's how binary conversion works. So if you're confused about this, I would tell you to go do some more research on it. But you know, this is pretty much the basics, and I think this does a pretty good job of explaining it. But yeah, if you're confused, you can watch a video on it also. But yeah, so let's continue. And so the same actually works for colors. So the pixel is equal to, in this scenario, right, we have a red, green, blue. So this pixel, or this image, would have 3 channels instead of 4. There's no A. And we're going to say the red is 123, green is 110, and blue is 255. So the higher the number, the more intensity of that color. And this is actually what the pixel would look like if with these RGB values. And so red is equal to 123, which is equal to this binary octet. Green is equal to 110, this binary octet, and blue is equal to 255, which you can see is all ones because that is the maximum number that an octet can equal, which is 255. And so we can see this pixel has the highest possible value for blue, and which is why it looks more blue than it does green or red. We are going to practice turning ASCII to binary, aka your characters that you type in into octets of binary strings. So the first thing we need to do is get our virtual environment set up. So I'm just going to type in Python 3 -m venv space, and I'm going to name my virtual environment .venv, enter. And while that is getting set up, we can just get started with programming. So I'm going to create a new file, and I'm going to call it ASCII _to _binary.py. And in here, I'm going to quickly define the message that we want to convert into binary. So I'll say message is equal to, and we're going to keep it short so that we can really see what's going on, and we're going to call it hi. And then we are going to say for character, well, let's actually first define what we want to do. So the first thing we want to do is turn these characters into integer or decimal. And then we can, see what their integer decimal values are that are associated with the characters. So let's quickly run a for loop over the message. So for character in message, right? We're going to use a function. So let's just print quickly called ORD or ORD. And so what ORD does is it turns a single character string, aka our character, into its integer value in ASCII. So we'll say ORD of character, and let's go ahead and enter our virtual environment. And then from here we can run our Python script. So when we run this, it's going to iterate over our message and print the integer value, or the integer value that is associated with ASCII to the console. So we'll go ahead and press enter, and we can see H is 104 and I is actually 105. That's pretty interesting. So let's go ahead and now let's create a binary list. So let's turn each of these into their own strings and put it into a list. So we're going to define something called the binary list, or a variable called binary list, and we'll make it an empty list or array. And then we're going to say for character in message So we're going to turn each character into its own binary string and then add it to this binary list. So we already know how to turn it into an integer value, but how do we turn that integer value into binary in Python? So I'm going to show you that very quickly. So we're going to print this again, and we're going to say format. So we're going to use the format function in Python, and we're going to format the integer value, so ord, of the character. Okay, and so we're formatting ord, and then we're gonna pass in a second parameter, and it's gonna be 0, 8, and b. So why 0, 8, and b? Well, in Python, this stands for the 0 means pad the left side of the binary string with zeros. So the 0 equals that. The 8 says if the string, the string needs to be 8 digits long, and the B says turn it into binary. So why are all of these necessary? Well, let's say, we pass in just 1, right? Or whatever the character is for 1 in ASCII. So what does 1 equal in binary? Well, 1 in binary would actually equal just 1, right? Because this is 2 to the 0, which is equal to 1. Well, we want to see the entire octet. We don't want to just see 1. So if we just passed in b with the character or the integer value 1, we would only see 1. So we want to see all 8 of them. So when we pass the 8 function, or when we pass in 8, it says, well, we need to turn the string into 8 somethings. So what do we fill that with? Well, we need to fill it with zeros. So now we get this octet of 1, 2, 3, 4, 5, 6, 7. Now we get this printed instead of just a 1. So this is how we actually print the entire octet, so that when we want to reverse it back into a integer value, it works that way. So now that we have it in binary, let's go ahead and see what they look like. So let's run this again, and we can see that it works great. We see that it pads the left side with a 0 to finish the octet, and we get they're the exact same, which we would expect, except for the I, which is 1 integer value higher, actually has a 1 at the end of its binary string, equating to 1. So it's 1 plus 0, 1, 2, 2 to the 4, 2 to the 6, 2 to the, 2 to the 3, 2 to the 5, and 2 to the 6. So that's what it's adding up to get 105. So now that we have seen how we can turn it into binary, right, let's actually add this to a list. So we're going to say binary list dot append this entire function. And so now if we print the binary list, we will see a list of our binary strings. Now let's go ahead and turn these back into integers. So let's say for binary string in binary list, we're going to print print, and we are just going to use the int function to turn our binary string back into an integer. So we're going to pass in the binary string, and we're going to give it another parameter of 2. And so what is this 2? So basically the 2 is saying it's telling the integer function that it should expect something in base 2. So base 2, and base 2 is 1s and 0s. So it's saying expect this to be a binary string and then turn it back into an integer. So then we can run this again, and we can see we get 104, 105, the binary string, and then we get 104, 105 again, which is the the actual integer values for the characters. So let's go ahead and now let's turn these back into characters. So all we need to do now is pass in the char function. Sorry, is it CHR? There we go, the CHR function. And we run this. Oh, forgot to print it. So let's print the char function quickly. And we will see we get H and I for each binary string. And then if we wanted to turn it back into our message, we simply create something here called message, output equals an empty string. And we can say output plus equals each character. So now when it runs over this binary list, it will turn the binary string back into an integer, and then the character, and then it will turn that integer back into a character, which will then append it to our output message. And then we can simply print output. Output. And now, voila, we get our message again. So what is the least significant bit? You know, what are we talking about when somebody says the least significant bit in a binary sequence? So remember, when we're talking about bits, we are referring to a single binary digit in a string. We read binary from right to left, and the binary digit with the index of 0 is the least significant bit because it only has two numerical values of 0 or 1, and that's the lowest numerical values it can be. So no matter what, it'll only change the integer or decimal value by 1. So we can see here's a binary octet, which is equal to 110. And the 0 here on the right, which is at index 0, also is considered the least significant bit. So if this were to change to a 1, then this number would actually equal 111. If this stays a 0, right, it's still 110. But if we were to change any other bit, it would increase more than by 1. It would increase more than 1, or it would decrease by more than 1. So that's why we consider this the least significant bit, because it doesn't change it by anything more than 1. So why is this important? Well, when dealing with images, the pixels turn into a set of 1, 3, or 4 decimal or integer values. Remember, because 1 is grayscale, 3 is red, green, blue, and 4 is red, green, blue, alpha. These are the channels. So if you were to change the least significant bit of each decimal or integer value of each color and then save it to the image, then the color difference would be so small that the human eye wouldn't be able to notice it. So here's an example, right? Here's the original image, and here is the altered image where we changed all of the red values, and we subtracted the red integer values by 1. And so you can see it's not detectable by the human eye, right? I personally can't tell a difference. If you can, then congrats to you, but you know, I could never tell a difference. So you know, it's really interesting that we can change the colors and it doesn't do anything to the image really. So what can we do with this? Well, we will be using red, green, blue for our examples, and every pixel has 3 values, right? Red, green, and blue, which are turned into their respective decimal or integer values, which are turned into binary. Well, we can turn the message's characters into binary strings as well, and we will hide the message in the image's pixels' least significant bits. So we're not actually hiding the text inside of the image, right? We're literally changing the colors in a way that will encode the message. So we're literally encoding a message into colors, which I think is really, really cool. So yeah, like I said, this will alter the image's color so mildly that the human eye wouldn't be able to distinguish between the original between the original and the one, this is supposed to be a 1 with the hidden message. So what are the actual steps we need to take to get there? So first we need to get the message, right? So let's say it's hi, H-I, and we turn the message into its respective decimal or integer values, and then we turn those into binary. So now we have a list of binary strings that represent our ASCII characters, right? So here is 104 and 105. So next we take 3 pixels from the image for each character. So H will get 3 pixels and I will also get 3 pixels. So we're going to have 6 pixels in total and 3 for each character in high. So next we need to break up the pixels into RGB or red, green, blue, and turn those into their respective decimal or integer values, and then turn those respective integer values into binary themselves. So here is exactly what that would look like. So we have pixel 1, 112, 145, 9, and then pixel 1 broken down into binary here. We do the same thing for pixel 2 and the same thing for pixel 3. And so these 3 pixels together will encode the letter H. And now you might be wondering to yourself, well, hey, this is, H is only equal to 8 binary digits. Why do we need 9? And we're getting there, I promise. Why do we need 9, colors to alter? So next, and we're getting there. So next we need to iterate over the message character's binary string. So for each binary character in the messages character, example H, we will put that binary digit as the least significant bit for the corresponding pixel index. So here we have pixel 1, and at pixel 1's red, right, we look at H at index 7. So we're going to say, remember, because we read binary from right to left, so we're going to take H at this index, and we're going to put it into pixel 1's least significant bit for the red color. We do the same thing for the next one, and then the next one. So you actually see that we don't need to change this pixel at all in order to encode these first 3 bits. The next time, for the next pixel, right, we do the same thing. We take this one, put it here, take this one, put it here, take this one, put it here, and we also didn't have to change pixel 2 at all in order to change the next, or in order to encode the next 3 bits. Well, when we get to pixel 3, we do see that this 0 is pointing to this 1, and that means we will need to change this 1. So pixel 3 was equal to, if we go back here, we had a 99 as its red value. Well, if we change this 1 to a 0, its red value is going to go to 98, and that will encode for this 0. So we're going to have to change this 1 to a 0, and then we can move on. And we can say that the pixel's green, or pixel 3's green value is a 0, so we don't have to change that one at all. And then we are going to continue on to the 9th bit. So here's where we need 9. So this is going to be called our continue bit. So if it's a 0, we need to keep reading, whereas if it's a 1, then the message is complete. So since H isn't the last part of the message, we leave this as a 0. When we get to I, right, we're going to change this to a 1, saying you need to stop reading the image, or I'm sorry, reading the pixels, because we have actually finished the message. So you can stop and turn everything into the message. So step 7 is, once you reach the final character, right, set the 3rd pixel's blue binary string's least significant bit, which is this one, right, pixel 3, blue, least significant bit, to 1. This tells the algorithm we will write that we have reached the end of the hidden message and to stop reading the pixels. So congratulations, you officially have learned what least significant bit steganography is and how, like theoretically, to encode a message into the colors of an image, which I, again, think is super awesome. So thank you for watching this one, and in the next lecture, I will walk you through and we can get started actually programming this in order to create our algorithm that will, or our program that will encode our message into the colors of our image. We are going to be setting up our program for image steganography. So I have this basic example image that we had from the other image manipulation video. So let's go ahead and get our environment set up. So I'm just going to create a virtual environment really quickly in this directory. So Python 3 -m vnv space .vnv. And while this is going, we can just go ahead and start coding. So let me quickly create our, we'll just call it steg.py. And this is going to be our main Python script file. So what do we need? So if we remember from our image manipulation video, we're going to need to import. We're going to need to say from pill import image, and for this one we're also going to need argparse. So we're going to import argparse. There we go. And we don't have Pillow installed yet, so we're going to activate our virtual environment. And we're going to do pip install and pillow. And while that's going, we can get our script started. So we're going to create our entry point first. So if underscore underscore name underscore underscore equals underscore underscore main underscore underscore, then run the main function. And we'll define main right here, def main. And the first thing you want to do is create our argument parser. So for this one, we're going to take in the -d for decrypt, -e for encrypt, -f for the input file, -o for the output file, and -m for the message. And those are the only ones. So like, remember, if we, for the metadata, we had a -mn for the metadata name or the metadata key name. We are not going to have that for this one. So we, without further ado, we can just start coding, and we can say parser. So let's create the parser object first, equals argparse dot argument parser, and we'll give it a description, which shows when we do the help function, or when we give it the help flag. And we're going to say script that hides a message or decrypts a message using least significant bit steganography with images. Let's just make sure I spelled that right. I did not. Steganography. There we go. And next we can start adding in our arguments. So the first one is going to be the decrypt. So parser dot add, and it doesn't matter, you know, in what form or in what way you add these, as long as they all exist. That's the important thing. So we're going to say -d for decrypt, and we're going to store it again as a true false variable. So we're going to say action is equal to store underscore true. So if the -d exists, then it will say true. If it doesn't, then it'll say false. So we'll say help equals option decrypt, and then we'll do the same thing for encrypt. So I'm just going to copy and paste this. And then we'll say, instead of -d, we're going to have -e, and instead of option decrypt, it will be option encrypt. And then we're going to say parser dot add argument, and we'll give it the -f for the input file, and we'll say required is equal to true, meaning it will error out if they don't give the -f flag with a value. And we'll say type is equal to string, and we will say help is equal to file input path. And then we'll say parser dot add argument, and this time we will give it the -o for the output file. We'll say required is equal to false, because we're not always outputting something, and we can say type is equal to string, and we can say help is equal to output file path. There we go. And the final one is the message. So parser dot add argument -m, and we're going to say required equals false, type is equal to string, and help is equal to the hidden message you want to encrypt in the image's pixels. There you go. And now let's quickly just run this to make sure everything is working. So we'll do Python stag.py from pill import image, and interesting, error cannot import name image from pill. Let's see if it's because our Python interpreter is, nope, it's our virtual environment. Aha, it's because I have a lowercase I. It needs to be a capital I. So let's run this again. Okay. Let's give it a dash F. Oh, I see what happened. We didn't actually parse our arguments. So we'll say args is equal to parser dot parse args. And now all of our arguments will be stored into this variable, and it will check to make sure that the dash F exists as well. So we'll do this now, and we should get an error. There we go. And let's do dash dash help, and we should get everything on how our script works. Perfect. So now let's just make sure everything is in the correct order, and then we can start filling in the blanks as we go. So we know how we want it to work, which is if not args.d or args.e, then we should error out because we need an encrypt or decrypt function. So parser.error. We say the script requires either a D or E flag. There we go. And we can say if args.d and args, if args.d, then we will run the decrypt for args.f. And then we'll say else if args.e and args.f and args, if args.e and args.o and args.m, then we will run the encrypt function on the input file, so args.f, args.o for the output file, and args.m for the message. And so let's just finish this off with an else, and we'll say parser.error, and we will say incorrect usage encryption requires a dash E dash F dash M, just dash M dash O and just M and O, flags to run. There we go. And now let's just fill this in with a simple print statement, or we can just say continue. Nope, we cannot. Let's just do a print, and let's do a print here. And we'll fill this in with encrypt, and we can say this one is decrypt. We'll save it, and now let's run our function, and let's give it a dash F of example.png. Let's give it a dash D as well for decrypt, and it'll run decrypt. And then if we do dash E, we should get an error. Yep. And then let's give it a dash M with the message, and then a dash O with output.png. There we go. It says encrypt. So we're just ensuring that all the flags exist for the function that we want to run. And so now that we have set up our script correctly, we're going to be creating the encrypt functionality. So it may be a long one, and it may get a little confusing at times, but I'll try my best to walk through everything that we're writing so that it's not as confusing, and I'm not going to use any shorthands or any of that. So we're going to leave it in pretty much, explainable code if you could say that. So let's quickly define the encrypt function. And right, so like, what are the things we need to do with the encrypt function? So first, we need to take the message and turn it into a list of binary strings. Right. Then the second thing we need to do, right, is we need to open the image that we have from the input file, make a copy of it. The third thing we need to do, right, so I'm just going through the list that I had detailed in our presentation, is we need to, then take 3 pixels at a time from the image, and we need to change, so step 4, or we can actually call this, step 3.1, because it'll be in a loop. We need to take the colors of the pixels and turn them into binary strings themselves, and replace the least significant bit with the message's character binary string index that we're at. Then we need to, so we're going to do that for every single image, and we're going to say 3.2 if end of message, or I'm sorry, we need to do that for every character in the message. And then at 3.2 we say if end of message, then change the least significant bit of the third pixel's blue value to a 1. And then if not, then we change it to, if not, we change it to a 0, meaning we continue the message. And then step 4 would be to save the image. So let's work through how we need to do this. So for the encrypt function, we're going to take 3 arguments. We're going to take the output file, message, and the input file. So we're going to say input underscore file is what we're going to take as the first one. We're going to take the message as the second parameter, and we're going to take output file as the third parameter. And then the first thing we need to do, right, is we need to take the message and turn it into a list of binary strings. So how can we do this? Well, I want to separate this out into a completely different function, and we're going to call this convert message to binary list. So we'll say def convert message to binary list. And it's going to take in the message, and it's going to run a loop over this message. So we're going to say first we're going to define the list. So we're going to say binary list is equal to an empty list. And we're going to say for character in binary list, we are going to say for character in message, we're going to say binary list dot append and then we're going to turn the character first, if you remember, into its integer value using ORD, and then we're going to format it into a binary string using the format function. So we'll encase everything in the format function, and we're going to give the first parameter of the format function ORD of character, and the second parameter of the function is going to be 08B, meaning, again, 0 turns or pads everything on the left with zeros. 8 will turn or ensure that our binary string is of 8 characters long, and B says to turn it into binary. And then we're simply just going to return the binary list. And so here we can say binary list is equal to convert message to binary list, and then we'll pass it in the message. And let's actually just print this binary list. So now if we scroll down here, we can replace this print statement with encrypt, and we're going to give it input file is equal to args.f. We're going to say message is equal to args.m, and we're going to say output file is equal to args.o. And now when we run this exact when we run the script again with these exact same arguments and we press enter, we should get a binary list for message. And we can see we have 1, 2, 3, 4, 5, 6, 7 binary strings, and message is 1, 2, 3, 4, 5, 6, 7 characters long. So it did work. Next, so let's just comment this and we'll say converting the message to a binary list. There we go. And then next, what we need to do is actually open up our image file. So we're going to open the image and make a copy of it. So we're going to say image is equal to image.open, and we're going to say input file as the path. So now we're opening the image using the Pillow library, and we're going to say, actually, we need to ensure that the image's mode is in RGB, so it has 3 channels. So the way we can ensure this is we're going to say image.mode does not equal RGB. So we're going to say if it doesn't equal RGB, then we're going to say image is equal to image.convert RGB. And so now when we're getting an image, right, if we open it, like for example, example.png is actually an RGBA, so it has 4 channels. It's going to convert that back to an RGB image so that we can easily do this without having that extra alpha value. So now let's actually get the width and the height of the image. And this is going to be very important later on because, and you'll see why. So we're going to say width height is equal to image.size. So we're going to need this width value later on because we're going to flatten our NumPy array. So we're going to say new image is equal to image.copy. And so now we're making a copy of our image. So we're copying the image. And then we're actually going to start taking, sorry about that, we're going to start taking the pixels and turning them into, and encoding our message in them. So now we can say current underscore pixel underscore x is equal to 0. And we're going to say current underscore pixel underscore y is equal to 0. And so now we're actually going to run a loop. So we're going to say for pixel list in perform lsb underscore steg. And this is going to be a function that we're defining, and it's going to yield pixel lists back to as its return value. So it's going to yield a pixel list. So we're going to say new image is equal to new image, and we're going to say binary list is equal to binary list. So let's go define this function now. So we'll go up here and we'll say def perform lsb steg. And it's going to take in the new image and the binary list. So the first thing we need to do in this function is to get the flattened list of the image's pixels. So to do this, we say pixels is equal to new underscore image get data. And so this is a pillow, or this is a function given to us by the pillow library, which actually, instead of giving us a two-dimensional array of pixels in a grid, it actually just turns it into a flat list of pixels, which is really very useful for us because we don't want to have to do some extra logic in order to group them by 3. So the next thing we're going to do, we're going to say is iterate over the binary list and change the pixels in groups of 3. So we're going to define 2 variables here. We're going to say pixel index is equal to 0, and we're going to say group size is equal to 3 because we want 3 pixels at a time. And so now we're going to say for index in range of group size, we're going to give it we're going to create a new variable called current pixel underscore list, which is equal to a empty list, and we're going to say I is equal to 0. So for I in range of group size, we are going to say current pixel list dot append pixels at pixel underscore index plus 1. So what's happening here? So we're saying for index in the range of group size, so index is going to be 0, 1, or 2, we create a new pixel list, and we say, we give it an I value is equal to 0, and we're going to say for I in range of group size, so then this I is going to be 0, 1, or 2, and then we're going to say current pixel list dot append pixels at pixel index plus 1. Oh, and I apologize. I did not mean to do in range of group size. I meant to say in range of length of binary list. That would have made no sense. So we're actually doing for index. So index is actually going to be the length, or it's going to go up to the length of the binary list, right? And for each index in the binary list, we're going to grab 3 pixels. So that's what this is doing. So it grabs, so for I in range of group size, which is 3, we're going to append the pixel at that current index. So then we're going to say new pixels is equal to a blank list, and we're going to say if index is equal to the length of binary underscore list minus 1, we're going to say that this is the end pixel. So or we're going to change this and say it's going to be the end of message, and we're going to say else new, and this is going to be the continue bit to continue reading the message during decryption. So end of message, so continue bit will equal 1, and this one is continue bit, or continue message actually, with the continue bit equal to 0. Now, how do we do this? So basically, let's just go over this really quickly again. So we're going to say if the index, right, which is this number here, is the length of binary list minus 1, meaning it's the final index in the binary list, right? So we have our binary list here. That would be equivalent to this one here. Then it's going to change our continue bit to equal to 1. Otherwise, it's going to, it will say our continue bit is equal to 0 when we do our changes. So now let's say new pixels is equal to, and we're going to make a new function here called change pixels colors least significant bits. And this function, which we'll just go ahead and define up here, let's do def change pixels, colors, least significant bits. And we need to give this 3 parameters. So we're going to say binary message, the pixel list, and the can continue. And we'll just actually call this the continue bit. So this function is going to perform the changes on the pixels least significant bits. There we go. And so here we're going to create a little function. So we're going to say binary message index is equal to 0. And we're going to say for pixel index in range of, spelled range wrong, length of pixel list. Then we're going to say new colors is equal to an empty list. And we're going to say for color value in pixel list at pixel underscore index. So what's happening here? So we're going to say we create a binary message index variable equivalent to 0, and we're going to say for pixel index in range of length of the pixel list. So our pixel list is what we're going to pass as the group of 3. So pixel list will be equal to a length of 3, which is the individual pixels, and each pixel is going to have 3 color values. So this is where we say, this is why we're saying a new colors list. We create that for each pixel index. So we're going to say for color value in pixel list at pixel index. This is getting each color. So if we were to print this, we would get basically the red, green, blue index or integer values. So we're going to say color binary is equal to convert integer to binary. So this is a new function that we're going to create, and we're going to pass it in the color value. So the red, green, and blue. So it's going to say for red, green, blue, convert each into its binary value, and then save it in this color binary variable. So we're going to go up here, and we're going to define the new function, def convert integer to binary, and it's going to take in the color value, and we are simply going to return format. And we don't need to do the ORD on this because it's not a character. So we just simply say color value, and we do 08B. And this will return the binary value for this color value. So now that we have the binaries for each color, and actually, you know, it's probably a good idea to test this very quickly. So I'm just going to go ahead and print here the color binary, and we can make sure that things are happening correctly. So let's actually do new pixels is equal to change pixels least significant bits, and we're going to pass in the 3 parameters, which is the binary message. So we can say binary message is equal to binary list, and we're going to give it the at index. So we're saying the index of our binary list, which would be something here. So it'll be like 0, 1, 2, 3. And then we are going to say the pixel list is equal to current pixel list. So our current pixel list, which we got in groups of 3, so we appended pixels at pixel index plus 1. Then we can say continue bit is equal to, and this one is the end of message, so it's going to be a 1. And then let's do the exact same thing. So let's just copy this, put it here, and we will say the continue bit for this one is actually equal to 0. So now, if let's just make sure there's no errors or anything. It appears this is expected indent block. Aha, because we are iterating over the pixel list and perform least significant bit. So we're actually just going to take out this 4 right now. We'll add it back, but we just want to test, and we'll get rid of this. And then we can go ahead and run our encrypt function. So we will -e, and this is correct, so let's quickly run it. And you can see we get a big list of the, so if we scroll up here, easier to explain, we're printing the color binary. So this is if we go up, we can see here's a group of 3, red, green, blue for the first one, for the first pixel, red, green, blue for the second pixel, red, green, blue for the third pixel, and this should be 3 pixels for every single character in our message, which I do believe it is. So now we can continue, and we can say if binary message index is equal to 8, then if can continue, or I'm sorry, if continue bit equals 1, then new colors dot append convert, and we're going to do a new function here, convert to integer from binary, and we're going to pass it in the color binary, and we're going to pass it in with 1, and we're going to say else new colors dot append, and we're going to do the same function, which we'll actually just define really fast. So let's say def convert to integer from binary, and it is going to take in the binary string, and we're going to return int binary string in base 2. So that converts it to an integer. And we're actually going to have to put another function in here as well. And we are going to create another function called change least significant bit. And it's going to be the color binary, and it's going to be 1. And we're going to do the same thing down here. And so what's happening here? So if binary message index is equal to 8, meaning the binary message index here, which is going to increment as we go through these. So if you're wondering like where the increment value is, it's coming, but we want to do it at the end, but we can just add it in now. So we'll say it goes here. Yeah, so for color value, and we can say binary message index is equal to binary message index plus 1. And so now we're iterating over every single color in our pixel list. So basically, the binary message index is keeping track of our binary message, which is, one of these here. So there's 8 of these, and we're saying if binary message equals 8, meaning we're at the 9th value, because remember, indices start at 0. So if we add 1, right, getting to 8 is actually the 9th value, which is our continue bit. So if continue bit is equal to 1, right, then we want to change the third pixel's blue least significant bit to 1, and if not, and it's continue, then we want to change it to 0. Sorry, I need to put a 0 there. So that is what this is doing. So we're handling that final continue bit in the message or in the character right now, and then we'll handle actually changing the least significant bit. So we're going to say now else. So if it is not at the continue bit index, then we will say new colors dot append, and we'll say convert integer from binary, and this is going to take the function change least significant bit, and this is going to take in the color binary, and it's going to take in the binary message at binary message index. So we're about to define this function here. And so let's go ahead and do that. We're going to say def change least significant bit. And it's going to take in the color binary, and it's going to take in the we'll just say LSB, so the least significant bit. And so to do this, we simply need to say binary list is equal to color binary, and we're going to turn this into a list. Click save. And so what does this do? We're turning this string, so the binary string, into a list so that it's easy to manipulate, because strings are immutable, so you can't change a current character in a string. So we're going to turn it into a list first, and then we're going to say, and we're going to store it in this binary list variable, and we're going to say binary list at -1 is equal to the LSB. So what is this meaning? So if you're working with lists, and here let's just quickly show something here. 0, we'll just say 0, 1, 2, 3. So when you're working with lists or arrays in Python, you can give it an index of a negative value. So if you give it at 0, it gives it, it'll be here, right at 0. But if you give it at -1, it'll actually start at the end of the list. And if you give it -2, it'll start at the list here. So we're changing the least significant bit in our color binary string. So it'll be, we'll just copy this. So we'll say this is a list, and we're changing this value. We want to change this value in the list. And now we have a list, but we need to turn it back into a string. So what we're going to do is just going to say return, and we're going to create an empty string, and we're going to say .join, and we simply pass in the binary list. And what this does is it turns our list back into a string, and then it returns it. So now we have changed our least significant bits for all of them. So we're saying if binary message index equals 8, and if the continue bit is equal to 1, then we change the new colors. Then we have a new colors list here, which are going to store what we change, and we append and we convert to integer from binary. Well, actually, let's just start here. So we're changing the least significant bit with the color binary and the bit we want. And then we convert that binary back into an integer, and then we append that into our new colors list. And then we do that for the same if the continue bit is a 0, and we do that the same if we're not on the continue bit and we're just taking the binary message at binary index, and this is going to be a bit. And then we increment our binary message index to continue on. So I know that might be a lot, but do just like study this and try to, figure it out if it's not like apparent right now. So now we can return pixel underscore list. And so let's actually print, right, our oh wait, I'm sorry. So we need to say, after all of this is done, pixel underscore list at pixel underscore index is equal to a new set, which is new underscore colors at 0, new underscore colors at 1, and new underscore colors at 2. So now that we have actually changed our colors to match the least significant bits that we need, we are saying pixel list, so this list here, at the pixel index, right, which is the length of the pixel list, so 0, 1, or 2 in this case. Then we change that to a new set, which is how it gets stored for images. It needs the set data structure. And we say new colors at 0, new colors at 1, and new colors at 2. So we're saving the new set of colors that have been altered with LSB steganography. There we go. And so we do that for every single pixel index, which is only 0, 1, and 2. And then this one at index 2 is going to be our continue bit. And then we return our pixel list. So now if we scroll back down here, we can see where we were performing the least significant steganography function. We have the if index is equal to this one, then we change it with the stop message. And if it doesn't, then we just give it with the continue bit. So now what we need to do is we need to say pixel index is equal to I plus 1 plus the pixel index currently. So what does that mean? So we're at I, and I is equal to 0, and we go and we increase it by the group size. And so then at the end of this, I is going to be equal to 3. And so we say I plus 1 and increase it by the pixel index. So now every time we go through this for loop, we're at the next index rather than for the pixels rather than the one that we were just working with. So next we just simply yield the new pixels. There we go. And so this is where we actually do our yielding. So we're iterating over the index for our binary list. We create a current pixel list, and then we append the current pixels into that pixel list. We create a new pixels list, and we say if index is equal to the length of the binary list at -1, meaning we're at the end of the message, then we will change our continue bit to 1, and we will change the pixels colors, least significant bits, to what we need them to be in sets of 3. Else we do the same thing, but we have our continue bit at 0, and then we increment our pixel index by 3. And then we yield our new pixels back to our function. So now we say for pixel list in perform least significant bit steganography, right? So this is the yielded pixel list of new pixels that we've altered. We're going to say for pixel in pixel list. So now we iterate over our pixel list, and we're going to say new image dot put pixel. And this function takes an x and a y coordinate as a set and also a pixel. So what we need to do is give it the current pixel or x pixel and the current y pixel. And then, so that's the first parameter. And we also give it just the pixel we're working with in the list. So for the pixel list in this, so every time this yields a new pixel list, this will happen, and then it will iterate over the pixel in the pixel list, which is only 3 pixels at a time. Right? Is it 3 pixels at a time? Yield pixels? Yeah, it's 3 pixels at a time. Then we put that into our new image. So we're replacing the pixel in our image copy. And then we're just going to say if current underscore pixel underscore x is equal to, and this is why the width was important, width, then current pixel x is equal to 0. So what this is saying is if we, let's just try to put it in a comment here. So we're working with a 2-dimensional array now. So we're trying to put this back into a grid state. So we have like 0, 0, 0, and then in here, and we'll do this, and then we'll say 0, 0, 0. So what this is saying is if our current x value reaches the end of the width, then we're going to reset the width, and we're also going to increase, so we're going to say current pixel y equals current pixel y plus 1. And then we're going to increment our y value. So we'll go across here, and then we'll increment the y value by 1. And so then we're working with this now, working on the next row, rather than, I do apologize, my cat has decided to bother me. And then we increment our y value. So if this doesn't occur, so let me just delete this quickly. So we're going to increment our y and reset our x value. Else the current pixel x is just equal to current pixel x plus 1. So now otherwise, if we're not at the end of the width, then we just increment our x by 1 until we do get to the end of the width. And then we simply will say, at the end of this for loop, we are at the final stage where new image dot save, and we give it the output underscore file. And we'll save this. Now, let us run our script, and we'll see if it works. So when we run it, it runs successfully, and we get our output image, which looks exactly the same as our example image, but it has our message actually hidden inside of the pixels. And in the next video, I will explain to you exactly how we can decrypt this now, and get our message out of our image that we've just encrypted. And again, I'm using a PNG because it has a lossless compression algorithm, whereas like a JPG will have a lossy compression algorithm, meaning it might alter our data. Let's quickly define our decrypt function. And decrypt is simply going to take the file. So we'll just say input file. And the first thing we want to do for decryption is, so first let's define what the steps are. So 1, we're going to open the input image. 2 is we're going to get, hashtag, get the image's data in a 1-dimensional array. Then we're going to iterate over groups of 3 pixels and decrypt the pixels. And then, that's step 3. And step 4 is going to be displaying the message. So let's do this. So first step is going to open the image. So image equals image. So the pillow library dot open with the image variable, or the input file. Input file. And the second step is to get the image's data in a 1-dimensional array. So get the pixels in a 1-dimensional array. So, and let's actually convert that to a list. So we're going to say pixels equals list. So we're going to turn our 1-dimensional array into image.get Metadata. And so now it has been turned into a list. And then what we're going to do is create a group size variable equal to 3. And we're going to say our message, which is going to be what we're going to display, is equal to an empty string. So now next we'll just say for index in range of 0 to the length of pixels, and we're going to skip by group size. So what is this doing? Oops, I'll just say cancel. So what is this for loop doing? Well, basically, if we have our list 0, 1, 2, 3, 4, 5, we're starting at index 0. That's what this 0 means. And we're going to the length of pixels. So if pixels is this list, which goes from 0 to 5, then this is the length that it's going to go until it stops. And group size is what it skips the index by. So we start at 0, and we're going to skip. So after we do index 0, it'll skip by 3. So 1, 2, 3, and it'll go to 3. And then it would skip by 3 again. And so that way we're gathering groups of 3 pixels, and then it'll start on the next iteration at the index after that group of 3. So that's why we're doing it this way. So we'll delete this. And then we're going to say character and continue flag are equal to decrypt character from pixel group. And we're going to pass into this function that we'll define in a second, pixels at index index plus 3. So what is pixels at index and index plus 3? Well, this is creating a subset. So it's slicing our slicing our pixels array or pixels list at index, which in our first one is going to be 0, and index plus 3, which would be the third index up. So that would be 0, 1, and 2, and then 3, but it leaves that last one out. So it goes up to this index. So we can also just say up or plus by group size, and it'll do the same thing. So next, let's define our function, decrypt character from pixel group, and it's going to take in a pixel list. Oops, sorry about that. Typo. And let's give us some more space here. And so with this function, the first thing we want to do is declare a variable called binary string and create that as an empty string. Then we're going to also give it another one called continue flag, and that's also going to be an empty string. And the third one is going to be called index, which is equal to 0. Now, next we're going to iterate over the pixels in the pixel list. So for pixel in pixel list, and then for each pixel we're going to iterate over their color. So for color in pixel, so that's the red, green, blue, we're going to say color list is equal to, and we're going to turn this into a list, convert integer to binary, and we'll pass in the color. So we're turning the color that we're on, so whether it's red, green, blue, for whatever pixel, into a list of a binary. So this is an integer value, 0 to 255, and it turns it into binary, and then it turns that binary into a list. So zeros and ones in a list format so that it's mutable. Or rather, it's just easier to manipulate. So we're going to say if index does not equal 8, then binary string plus equals color list at -1. So we're saying binary string for our character, so we're decrypting the character from this pixel group, is appending onto the end of the current binary string color list at its least significant bit. So what it should be. And then we're going to say index equals index plus 1. But if we're at the 9th bit, we're going to say the continue flag is equal to color list at -1. And then we will say character is equal to the char function inside of the int function with the binary, or I'm sorry, the int function inside of the char function, turning the binary string back into an integer because we're passing the binary string and the number 2, or the integer 2, which says which is telling the int function that it should expect a binary string in base 2 format, and then it turns that integer back into its ASCII character. And then we can simply return the character and the continue flag. This video is going to be monumentally shorter than the previous one, just an FYI. So now that we have returned our character and continue flag, we can say we can say the message is equal to message plus character. So we're appending that character onto our message. This could also be written as message plus equals character, but whatever. And then we simply need to say if continue flag equals 1, the character 1, then we break our loop and we have our message. And then the next thing is we need to print f, so format our string, decrypted message, and we can just say our message. And it's as simple as that. So now let's go ahead and do Python -d for decrypt and -f for our input file, which is output.png. And let's see if we get our message. Oops, I actually totally forgot to replace this print decrypt. And let's actually run this function here, decrypt args.f. And let's run it now. Something has occurred. Oh, I apologize. I ran the wrong script. So we want to do -d and -f output.png. There we go. And we get our decrypted message of message. And we can prove that this works if we do this, and we are going to change the message to, this is the coolest thing I've ever written in Python by far, exclamation point. And then we can decrypt it again, and we can see that our message is, this is the coolest thing I've ever written in Python by far. So congratulations, you have officially created your first image steganography program using least significant bit methods in Python, and you are officially a cool person. Setting up the full steganography program. So without further ado, let's open up our terminal and let's set up our virtual environment. So we're going to say Python 3 space -m venv for virtual environment and .venv, and press enter. And while that is setting up, let's go ahead and create our main program. So we're going to say, let's call this steg program.py. And so what this is going to do is it's going to take in the file data, image, and audio steganography programs that we've already made and turn it all into one. So this is just the setup. So first thing first is let's import argparse into our program, and then let's also create the entry point. So we're going to say if main equals main, then run the main function. And let's say def main, and so we're going to just define our main function, and then the next thing we need to do is create our parser, our args parse, our parser object. So we'll say parser equals arg parse dot argument parser, and we're going to give it a description of, let's say, the script that performs Steganography on GIFs, images, and audio files. There we go. And then next, let's start adding in all of our arguments. So we're going to need every argument that we had before, including a new argument for type. And type is going to define our, PDFs, images, or audio. So let's say parser dot add argument, and then we're going to do -d, and then we're going to store this as a true or false. So action equals store underscore true, store true, and help is going to be option encrypt. Do the same thing for encrypt, so we'll just go ahead, copy this, -e, option encrypt. The next one is going to be our type, so parser dot add argument, and we're going to do -t. We're going to say this is required, and we're going to say the type is equal to string. Oops. Type is equal to a string, and we're going to say help is equal to the type of file, that Steganography will be performed. There you go. And then next one is parser dot add argument, and we're going to add in a file, so -f, required is equal to true, type is going to be equal to string, and we're going to say help equal to the input file path. Then we're going to say parser dot add argument, and now we need the output, so -o. We're going to say this is required is false. Type is going to be equal to string. And then we need the help equal to output. Then we're going to do parser dot add argument -m for our message. We're going to say required equal to false. Type is equal to string, and help is equal to message you won't hide. Next argument, and our last argument for now is an argument going to be our mn, so -mn, and this is going to be our metadata name. So we're going to say required is equal to false, and type is equal to string, and help is equal to the metadata key name. And we're going to say this must start with a slash. Yep. And now that we have all of our arguments, we can say, we can actually parse them. So we can say args is equal to parser dot parse args. And we can say if not args.d or args.d. Then parser.error script requires either a -d or -e flag. So if the user doesn't give us a decrypt or encrypt flag, then throw an error, and then if args.d, then we're going to decrypt. If args e, then we're going to say if args.o and args.m, then we can run the encrypt function. So we're just going to put encrypt here now, and we'll say else parser.error, and we will say script requires e-o -o and -m command or flag for the encrypt. There we go. And then we will say else. Actually, I don't think we need to do that. There we go, and that is all for now. So now let's actually create our encrypt and decrypt functions, and we can explain a little more how they're going to work. So let's start with encrypt. So we'll say def encrypt, and this one is going to take the, first of all, type, then it's going to take the input file, the metadata name, the message, the output file, and the parser. Lots of lots of parameters, I know. So we're going to say if type, right, to the type of file is equal to PDF, then we're going to say if metadata name, meaning if metadata name exists, then we're going to print encrypt with PDF file metadata, and we can say else parser.error PDF requires the -mn flag to run. So we're saying basically if the metadata name does not exist, then check an error saying that it requires the mn flag to run. And then we're also going to do the same for images and audio. So we're going to say if type equals image, and print encrypt image. And we'll say if type equals audio, then we're going to print encrypt audio. There we go. And then we'll say else parser.error the only types acceptable are PDF, image, and audio. There we go. And so now, if we go ahead and remove this, we can say encrypt args, we're going to say type is equal to args.t. We're going to say input file is equal to args.f. Next, we're going to say metadata name is equal to args.mn. Then message is equal to args.m. And output file is equal to args.o. And then lastly, parser is equal to parser. So that'll pass everything in. So next, let's enter in our virtual environment. So .env script /activate. And here we can run our Python script. So let's run Python stagprogram.py, and we'll practice the encrypt function. and we'll go to File. We can say example.png, and let's use the you know what? Actually, let's do a PDF. So we'll do boring data. Not that it actually matters right now, but because we want to keep it correct, and then I don't have to do very much when I don't have to type it all out next time I want to encode a message in the PDF. So we're going to do that, and we're going to do -mn, and the metadata key name is going to be /key, and then we want the -m for the message, and the message can just be messages are cooler hidden. And we can do, what's the last one? Oh yeah, -o, which is the output.pdf. I think that is everything we need. It will let us know. And raise type error message. Oh, you know what? I think I forgot the type. So -t for type, and then we need to give it a PDF. And press enter. And we get another error, and it's saying in add argument. Aha. There we go. We got a -f, and let's run it again. And now we're seeing encrypt with PDF file metadata. And so what happens if we don't add in the metadata key name? It should toss us an error. And yes, it does. Steg program by error. PDF requires the -mn flag to run. Perfect. And then if we try the same thing, let's just change the type here to image. We get encrypt image. Perfect. And if we do audio, we should get encrypt audio. There we go. Awesome. So now that we have our encrypt function semi-working, let's go ahead and let's create the decrypt function. And this one is simply going to take in the type, and it's also going to take in the input file. There we go. And we're going to do the same thing here, so we can copy and paste. Except we don't need this. And we're just going to print PDF. Decrypt image, and then lastly, we want decrypt audio. Oh, and actually we are going to pass in the parser. There we go. And so now instead of print decrypt, we can actually say decrypt and pass in the type is equal to args.t. We can also say input file is equal to args.f, and lastly, the parser is equal to parser. Awesome, and now let's try to decode, just to make sure everything's working. Audio works, decrypt PDF works, and let's decrypt the image. That one also works. Awesome. So now that we've got everything set up for our program, the next thing we need to do is fill in the blanks, and we're going to create classes for all of the other files that we already made. We are actually going to be creating the full program now. So if we look over here, we have some things to fill out. Let's actually create a new folder in our directory, and we're going to call this steg_classes. There we go. And in steg classes, let's go ahead and create a new file, and we're going to call this file_metadata.py. So we'll just start with file metadata. And so actually what we're going to do is, if we go and pull up our old file metadata program, we can simply grab everything until the main function. So don't copy the main function, but everything until then is okay to grab. And let's paste it in here. And then let's also get the import of PyPDF2. So if we go back, you can see here it is, and let's grab PyPDF2. Awesome. And we also need to do pip install pypdf2. And then while that is installing, let's actually turn this file into a Python class. So let's say class, and we'll call this file metadata. Or actually, let's call this PDF file metadata. And let's add a colon. And then let's just indent this encrypt and decrypt function. There we go. And so now we have pypdf2 installed, and let's go back to our steg program. So here we're going to say import steg classes dot file metadata, or I'm sorry, we're going to say from. So steg classes is our directory name. File metadata is the Python module. And we're going to say import, and we're going to say file, or PDF, file metadata. And now if we're going to replace this print statement with PDF file metadata dot encrypt. And we're going to pass in the input file is equal to input file. I apologize if you can hear meowing in the background. That's my cat. And then we're going to, what else do we need to pass in? We also need to pass in the metadata key name, the message, and the output file path. So let's go ahead and say metadata key name is equal to the metadata name. And we're going to also say the output file path is equal to the output file. And then also the message, comma, message is equal to the message. And so now what we can do is run our Python program. We're going to say, actually, I'll just type it in from scratch. Let's say Python steg program.py-e. The type is going to be PDF, and the file is going to be boring data.pdf. The message is going to be, here is a message, and the output file is going to be output.pdf. And I'll press enter, and it will run, and we will see, oh, there is an error. It requires the metadata name flag. So let's quickly do -mn, and in quotes, we will do /key as our metadata key name. And we got an error, got an unexpected keyword argument input file. So it actually expects file path, my fault. So let's go ahead, delete this, and type file underscore path equals the input file. And next we can run our program, and we can see the message was hidden successfully in output.pdf. And now we can do the exact same thing for the other files. So next what we need to do is the exact same thing we just did, but for the other files. But actually first let's change our decrypt, and we're going to say, instead of that, let's do PDF file metadata.decrypt with the, let's go look here, what does it require? File path. So file path equals input file. Save, and now let's run the decrypt function on our PDF file. So we're going to say -f is output.pdf, and instead of -e, we're going to do -d for decrypt, and we're going to get, here is our key with our message. Awesome. So now let's close out a file metadata, and in our steg classes directory, we're going to create a new one called image steg.py. So next we need to open up my command prompt, and I am going to open up the image steganography program we made. Here we go. And I am going to copy everything except for main and our entry point. So start here and just go up, and we'll paste it into our file here. Scroll up, and we'll get rid of argparse. And so we still need to import pillow. So we're going to say pip install pillow. And while that is installing, let's turn this into a class. So we're going to leave all of these functions outside of the class, except for encrypt and decrypt. So I'm going to take this function, decrypt character from pixel group, copy that, and I'm going to put it up here, right above encrypt. And I'm going to put encrypt and decrypt inside of our class. So I'm going to say class, we're going to say image Steganography, colon, and then I'm going to simply tab these, and now we have made our class for image steganography, and they have access to the functions in this file. So let's go back to our steg program, and let's change encrypt image to, first we need to import it, sorry. So we're going to say from steg classes dot image steg import image steganography. There we go. And let's quickly say image steganography dot encrypt. And what does the encrypt function take? The encrypt function takes the input file, the message, and the output file. So we're going to say input file equals input file. The message is equal to the message. And the output file is equal to the output file. There we go. And now let's run our Python program on with our new encrypt function. So for image steganography, so we'll do -e for encrypt, -t for the type of image, -f for, let's do, which one was it? It is example.png, and -o for the output file, which will be output.png, and -m for our message, which is this isn't a pixel, question mark, enter. So we can't find main module in steg classes. So let's quickly take a glance at what might have happened here. Don't know why. Oh, I see. I tried to run steg classes, not steg program. So I want steg program.py. There we go. Now when we run it, we can see that we get output.png. Perfect. And now let's run let's create our decrypt function. So under decrypt, we can get rid of this one. And we're going to say image steganography.decrypt. We're going to say file, or input file, I think is what it requires. Input_file equals input file. And we're just going to quickly go here. And decrypt takes input file. Yep. And now let's go ahead and say Python steg_program. .py -d for decrypt, -t for the type, which is image, and -f for the input file, which is output.png. We press enter, and we get our decrypted message, which is this isn't a pixel, question mark. Perfect. So this one works. So last but not least, we have audio. So let's go ahead and open up our audio steganography. Do that really fast. There it is. And here's our audio steganography. So we're going to do the same thing. We're going to take everything except for the main and the program entry point, and we'll copy it all. And in our steg classes folder, we're going to create a new file called audio steg.py, and we're going to paste everything in here. And we'll go up and we can delete our argparse. There we go. And we can we still need to install numpy and scipy. So we're going to say pip install numpy, comma, scipy. There we go. And while that is occurring, we can go ahead and turn this into a class. So same thing, we only want to put the encrypt and decrypt functions into our class as functions. So we're going to take these two, and I'm going to move them up here above Encrypt. There we go. And now I'm going to create a class, and I'm going to call it audio steganography. And it's just going to take these two functions, encrypt and decrypt. Perfect. So now if we go back to our steg program, we're going to import this. So we're going to say from steg classes dot audio steg import audio steganography. There we go. And we can see that our scipy and numpy have been installed. So next we need to do our encrypt functions and decrypt functions. So we're going to say audio steganography dot encrypt, and it's going to take the input file, message, and output file. So input file equals input file, the message is equal to the message, and the output file is equal to the output file. Perfect. And so now let's run our program again. Okay, we'll just do Python steg program.py -e for encrypt -t type of audio, and then we're going to do the file of song.wave, and then we are going to do the output file of output.wave, and let's give it a message of I can't hear this period, and let's press enter. That should create our new audio file. There we go, and we get output.wave, and it works. So next, let's create our decrypt function. So instead of print decrypt audio, we're going to say audio steganography dot decrypt, and this only takes the input file and input file. There we go. And now if we run this again, let's just delete everything and do -d, -t is audio, and -f is output.wave. We get the decrypted message of I can't hear this period. Perfect. So congratulations. We have turned our 3 separate steganography programs into one large steganography program. So next, what we're going to be doing is going over the theory of turning a file into a binary stream and then hiding that inside of our 3 methods as well. And then after the theory, we will move into actually adding that theory into this program, this large program right here, so that we can hide those, hide files inside of our other PDFs, PNGs, and WAV files. Firstly, what can we do is we can actually read a file in binary with Python. So when reading a file in Python, you can open it in binary mode to get the bytes of the file. So one cool thing about bytes is 1 byte is actually equal to 8 bits. Notice anything? Well, a byte is the same number of bits as our ASCII characters, meaning we don't really need to change our scripts that much when we're doing this. So for least significant bit on the images, we can just, instead of reading through the characters, right, and turning that to binary, instead we're just going to read through the bytes, turn that to binary, and we can do the exact same thing because, right, every single 8 bits is the same as the ASCII characters would have been. So for steps, we're simply going to read the file in bytes. We're going to break down the bytes into binary strings, and then we're going to place the binary strings into the file the same way we have been using least significant bit, or for the PDF metadata, we can just put the binary string in the metadata. We're going to be actually implementing how to encode our file into the metadata of a PDF file. So without further ado, we're in our Steg program, right? We have the encrypt and decrypt function. So we're going to actually have to add in another argument. And so we're going to say new argument for hiding a, oops, I'm in caps locks. So we're going to say new argument for hiding a file. And we're going to say parser.add argument. We're going to pass it in the -hf, which is going to stand for hidden file. And we're going to say required is equal to false, type equal to string, and help is going to be equal to the file path for the file you want to hide. There we go. Sorry, 1 second. There we go. And next, we will actually update a few things here. So we're going to say and args instead of just .m. We need and args or args.hf, so for hidden file. And we're going to pass in the hidden file here. So we're going to say hidden file is equal to args.hf. And then we're going to say requires the -m or -hf flag for the encryption function. There we go. And now let's head up to our encrypt and let's actually pass in the hidden underscore file. And so now for our encrypt function, we see if metadata name, else this. We are going to say if metadata name and message. We can do this one. Else if, oops, metadata name and the hidden file. So if hidden file exists or message exists, then we're going to do PDF file metadata. Actually, let's go and make that quickly. So basically what this is saying is if the metadata name and the message exist, then do this. But if the metadata name and the hidden file exist, then do this function, which we're actually going to write right now. So let's go back to our file metadata.py, and we're going to add two new functions, one called encrypt file and one called decrypt file. So let's go ahead and create def encrypt underscore file. And we're actually going to need the file path, same as the one above, and the metadata underscore key name. And instead of message, it's going to be hidden file, and also the output file path. So almost the exact same that we have above, and we're actually just going to copy this bit, paste it here. And instead of message, right, we are going to say, very quickly, we're going to so we're going to create a new variable called binary list, and we're going to set that equal to a list. Empty list, and then we're going to actually open up our file in binary mode. So we're going to say with open, and we're going to say hidden file, right, the one we passed, and we're going to put it in RB mode, so read binary, and we're going to say as HF, so as hidden file, and then we're going to say file underscore bytes is equal to hf.read. And so we're actually reading the bytes now, and we're storing that in the file bytes. So this returns a list of our bytes, and we're going to say for byte in file bytes, we're going to say binary list dot append, and we're going to format the byte into 0, 8 in binary. So this is going to be a binary string of 8 digits with left padded zeros. So what does, when we look at the bytes and we say 4 byte in file bytes, this actually returns an integer value, so it's not like a character or anything, so we don't need to use ORD. So it passes the integer here, which is the byte, and then it formats it into our binary, and then we append it to our binary list. The next thing we need to do is we're going to say hidden message is, or rather just message, is equal to reader, or I'm sorry, to empty string dot join, and we're going to say binary list. So basically the binary list is going to turn into a large string, and we're going to store that as the message. And so now we actually are able to just store it where we want to in the metadata. So if we now run our program, we should do pdf file metadata dot encrypt underscore file, right? We did save it that way. So yep, encrypt file. Let's give it the file path is equal to the input file. Then we also have the output file path is equal to the output file. Then we need the metadata key name, which is equal to metadata name. And then we have finally the hidden file, which is equal to hidden file. And then that will run and encrypt our file. So let's try it out really quick. We'll say Python. Oh, well, actually, we need a file to encrypt it in. So I'm going to close that, and I'm actually going to delete all of my outputs really quick. So I'll delete output.pdf, output.png, and output.wave. I just named them all output because it's easy to know which ones are already encrypted. So let's run this now. Python steg program. Let's do encrypt. The type will be PDF. The input file is going to be boring underscore data.pdf. We're going to say the output file is going to be something, or we'll just call it output, sorry, .pdf. And then the hidden file is going to be a new file that we'll make, add a new file, and we're going to call this text.txt. And so text.txt, we're going to say this is a cool hidden message, period. And we'll go ahead and close this. And now we can give it text.txt as the hidden file parameter. And I believe this should work. Oh, no, it's not going to, because we need the metadata key name, so mn. And we're going to give this as /key. Press enter, and we will see we now get output.pdf. And so if we click on it, we can now see here is our key, and here is our file actually stored as a binary string. So cool. So now let's work on decrypting this. So if we go back to our file metadata, we're going to create a function called decrypt file. So if we go here, enter, and we're going to create a function def decrypt file. And we're going to give it the input file path, the output file path, and also the metadata key name. And so for this, we're going to say with open the input file path, and we're going to read it in binary mode. All right, we're going to say reader, so we want to read the PDF's file metadata, pi pdf dot pi pdf2 dot pdf reader. Here it is, and we're going to pass it in. Oops, I forgot to say as file, and we're going to pass in file as the parameter, and then we're going to say metadata is equal to reader dot metadata. Okay, and then we're going to say save. actually, let's do a loop. So we're going to say for item in metadata, if item equals metadata key name, then save the file. And we're going to create a function called save file here in a second. And now let's actually create a flag, and we're going to say flag. We're going to say found flag, actually, equals false. And if we do the save, let's go here, and we'll say found flag equals true. And then what we can do is if found flag equals false, then print sorry, that metadata key name was not found. There we go. And so now let's create our function save file. So basically we're saying if we found the metadata key name in the metadata, then we send this found flag to true. But if it's false, then we print sorry, we couldn't find that metadata key name. So the user isn't expecting anything. So if we scroll up, let's create this function outside of the class. So def save file. And this is going to take in our binary string, so binary string, and also our output file. So now we're going to put this in a try except because things might get interesting. If we don't, it'll error out, and then our users will have no idea why. Exception as E, and then we will say print F. So we're going to format our string, and we're going to say an error occurred, colon, and then we'll put the stack trace in it as well. And so here we can say if the length of binary string, if the length of binary string modulus 8, if you don't know what a modulus is, basically it's saying if binary string's length is not divisible by 8, so we're saying does not equal 0. So if some number is divisible by the modulus, then it will equal 0. So if binary string's length is divisible by 8, meaning if it can be divided by 8, then it will equal 0, and it is an integer value, so it doesn't have a decimal. Then we're good. But if it doesn't equal 0, then we have a problem. So we're going to raise a value error, and we're going to say binary string length must be a multiple of 8. There we go. And then we can say, now we want to get our bytes. So we're going to create a new variable called byte chunks, and we're going to set this equal to an empty list, and we're going to say for I in range, and we're going to start at 0, and we're going to go to the length of our binary string, and we're also going to skip by 8 because that's how long a binary, like how long our bytes are. So then we're going to say byte chunks dot append, and we're going to get the binary string, and we're going to slice it from the current index to the index plus 8. And then it will, now it's going to run over our binary string, and it's going to get all of the bytes out of the binary string and put it into a list of bytes called byte chunks. And next, we're going to say byte list is equal to this. So now we need to convert those binary strings into actual bytes. So we're going to say for byte chunk in byte chunks, byte value is equal to int byte chunk, and it's going to say in base 2. So now we're turning it into an integer value, and then bytes list, byte list, dot append the byte value. There we go. And then, so now that we have them back into actual bytes, which are represented by integer values, we can say file bytes is equal to, and then we're going to turn them into actual bytes, the byte list. There we go. And so now we have a file bytes, which is equivalent to our list of bytes. And then we just simply say with open the output file in write binary mode as file. We can say file.write the file bytes. And we can click save. So now it will read and look for our metadata key name, and then it will pass into this file the binary string and the output file, and then it will say with open output file, and it'll turn all of our binary string into chunks of bytes, and then it'll turn those bytes into integer values, and then it will write it to and then it'll save it into a big data structure of file bytes, and then it will write it to our file as whatever we declared it as. So now if we go back to our main program, we're going to have to edit our decrypt function slightly. So if we go back down to here, we're actually going to pass in a new value into a couple new values. So we're going to have the output file is equal to args.o. So we're going to reuse our output file parameter, and we're going to say metadata name is equal to args.mn. So now we'll actually be passing in the metadata name into our decrypt function. So let's go up here, back to our decrypt function. Let's say the output file is equal to, or output file, sorry, and then the metadata name is also going to be added to it. So now we're going to say if output file, then we want to run a different, or our decrypt on the file, else we can do our normal decrypt for the message. Tab, and now we're going to say file metadata, PDF file metadata dot decrypt file, and we're going to pass it in the input file path, which is the input file. Next, we're going to pass it in the output file path, which is the output file, and then we're going to pass in the metadata key name, which is the metadata name, and then we're going to pass in oh nope, that's all. So that's all we're going to pass in for our decrypt now. So next, when we do Python in our stag program, and we pass in the decrypt parameter, and we say type is PDF, and we say the file is output.pdf, and we say the metadata key name is /key. Then when we press enter, oh, you know what? I didn't give it a output file name. Seeing this now. So it's going to decrypt normally. So let's give it the output file. So -o, and we'll say fun.txt. There we go. And so now it'll read, okay, so here we go, type error, say file. Oh, I see. So in our file metadata, I forgot to actually pass in the arguments here. So we need to give it the binary string. So this was binary string is equal to metadata at item. There we go. And then we also need to give it the output file, which is equal to our output file path. Perfect. And now when we run our function, or our script, we can see that we get an output of fun.txt, which is, this is a cool hidden message. So yeah, congratulations. You have now officially created a script that will turn any file, so it doesn't matter what file you give it, into a binary string, and then it'll save that in the metadata of a PDF file. And then you can also decrypt that and turn it back into the file that you want it to be and read it. we are going to actually be creating the algorithm to encrypt and decrypt the images, encrypt a file into the image using least significant bit and also decrypt it. So let's get started. The first thing we want to do, and by the way, this is going to be really easy, I promise. But the first thing we want to do is head over to our image steg.py, and we're going to literally copy our encrypt function. Okay. And we're going to save it as a whole nother function right below it. And instead of message, we're going to change it to hidden file. And we're just going to replace this line with a different line. And let's just replace this with hidden file and turn it into a list of binary strings. And then we're also going to say otherwhere if end of message. It's fine. We don't really need to worry about the comments. But basically, let's take this, and what we need to do is we're going to create a variable binary list and just create it as a empty list, and we're going to say with open hidden file, and we're going to open it in read binary mode as hidden file. We're going to say file bytes are equal to hidden file.read. So we're actually going to read the bytes now. And then we're going to say for byte in file bytes. We're going to say binary list dot append the byte. There we go. And now that's it. That is literally the only thing we need to change for our encrypt function. So let's actually see this in working. So we're going to say Python. Oh, shoot, actually, sorry, we do need to change one more thing. If we go back to our steg main program, we need to say under image, if hidden file, then do something else, do the message. So we'll do that, but we're going to say image steganography dot encrypt underscore file. I forgot to rename it. Whoops. So encrypt, and we need to change this to file. And then we go back here, encrypt file, and we pass in the file, input file is equal to the input file. The hidden file is equal to the hidden file, and the output file is equal to the output file. There we go. And now let's go ahead and say Python steg program.py dash encrypt. The type is going to be image. Let's say the file is, sorry about that. The file is example.png. And then the output file is going to be output.png. And I don't know if we need anything else. Oh, yes, and we need the hidden file flag, and that's going to be text.txt. And let's press enter. And we get an issue type error int object is not subscriptable. So where is this happening? New colors. Let's go to image steg. And let me see here. Binary list is equal to binary list. Yep, that's correct. For pixel and pixel list. So this is happening line 38 in change pixel colors. Least significant bit. Is there something wrong with my binary list? Let's see what happens if we print the binary list. No, so the binary list looks fine. Oh, wait, actually, you know what? It does not look fine. We didn't format it into binary. So let's say format the byte, and we're going to give it 08B. There we go. So we turned it into binary. Can't believe forgot to do that. And now let's run our script again, and we can see it all works well, and we get our output.png, which looks almost the exact same as example.png, but it is not detectable by the human eye that we actually encrypted an entire file into this file's colors. So now let's go ahead and create our decrypt function, which is also extremely easy. So we're just going to copy our decrypt function, and we're going to change this to decrypt underscore file, and it's also going to take in a output file. There we go. And the next thing we need to do is copy. So we have this function here, decrypt character from pixel group. So let's go find that. And literally all we need to do is copy this as well. Enter. And we're going to say, instead of decrypt character from pixel group, we'll say decrypt binary string from pixel group. And let's just delete this here. And instead of returning character continue flag, we're just going to return the binary string. So it does the same thing. It'll find the binary string in terms of 8, and it will return the continue flag. So if we scroll back down to our decrypt file, we're actually going to, instead of message, we're going to call this full binary string is equal to a random string, or an empty string, and we're going to say this is all good, and then we're going to change character to binary string, and then we're, instead of decrypt character from pixel group, we're just going to say decrypt binary string from pixel group, and instead of message equals message plus character, we're going to say full binary string plus equals binary string. So we're going to take every binary string from this decrypting the pixels, and we're going to add it to our full binary string, and then we will continue. So instead of displaying the message, we actually want to save the file. So if you remember correctly, we already created this function in the file metadata. So let's just scroll up here, and we literally just have to copy this save file, and we will paste it in here right above our class. So here's class. And let's save it here. Done. And then let's scroll down, and let's say save underscore file. And we're going to pass in the binary string, which is the full binary string. And then we also just pass in our output file. And we're done. That's it. That's all we had to do. So if we go back to our Steg program now, under decrypt, we're going to say if output file, then do what we just described, or what we just made, else we're going to do the normal one where we print the where we print the message. So now we're going to say we say image steganography dot decrypt underscore file, and we're going to pass in the input file, which is equal to the input file. Input file, and the output file, which is equal to the output file that we passed as the user. So now let's go ahead and decrypt our function, or decrypt our file. And so let's say output file is going to be output.txt now, and the file that we're inputting and trying to decrypt from is output.png, and instead of -e, we want to do -d for decrypt, and we press enter, and we see we get output.txt, and we get our message. What? That is so cool. So I'm going to delete all my outputs really fast. And so do be careful. So when you're using this functionality, right, I haven't added in anything to check if the file size is too big for the number of pixels in the image. So if your file size is too large for the number of pixels, you're not going to be able to do it. And we can test that right now. I'm actually very curious to see if boring data will actually fit inside of example.png. So let's do that right now. So I'm going to delete all my outputs really fast. Fun.txt. Let's delete that. And I'll just close my Steg classes. And let's actually encrypt this inside of our image and see if it works. Yep, this is actually correct. So the file is going to be PNG, output.png, and the hidden file we're going to change to boring_data.pdf. Enter. And so let's see. Yes, so it's out of range. Unfortunate. So there's too many bytes in boring_data.pdf to be stored in our example.png. And that's okay though. Still cool. So that is something to be wary of. In this one, we are going to be finishing up our Python script by adding in the ability to encrypt a file into the audio section. So without further ado, let's go check out our audio class. So let's go to audio steg and let's see what we need to change. Just like how images were, this is also going to be extremely easy. So let's go ahead and just copy our encrypt function. And let's paste it. And we're going to change this to encrypt_file. And we can leave everything the same, except we need to change this binary list here. And if we just literally go to image steg and we go to encrypt file, it is going to be this exact bit of code. And we'll go to audio steg, and binary list is going to be turned to this. And we just need to change message to hidden_file. And that's it. So now we have done it for our encrypt file. So let's go to steg program and let's edit this here. So we're going to say if hidden_file, then let's do ours. And if it's not a hidden file, then we can just do the message. So let's say, or we can do the file one. So audio steganography.encrypt file. And we're going to give it the input file is equal to input file. The message, the hidden file is equal to our hidden file. And the output file is equal to our output file. And that's it. So let's actually see if we can, encode boring_data.pdf into our audio. So let's see here. So let's do Python. Steg program. Let's do encrypt. Our type is going to be audio. And then our input file is going to be song.wave. Our output file is going to be output.wave. And then our hidden file is going to be, let's see here, boring_data.pdf. So let's see if our audio file is big enough to store boring_data.pdf. So let's run it. And sure enough, it is. So now we get song.wave, and it will sound exactly like output.wave, and we have actually hidden boring_data.pdf inside of our output. So if we go back to our steganography program, let's create our decrypt function. And so if we go to audio steg, let's go ahead and copy our decrypt function. And let's go ahead and make this decrypt_file. And we need to add in one more parameter, which is output file. And then the only thing we need to change, right, as before, is instead of message, we're going to say full_binary string. So this is going to contain the entire binary string for our hidden file. And then instead, so we have read group, right? So let's go find our read group function. Here it is. And we literally just need to change it so that it returns the binary string instead of the character. So we can delete everything except for binary string. And then we're going to change this to read group to binary string is what we're going to change our function name to. So if we scroll back down to our decrypt file function, we can change a read group to binary string. And then instead of character, we're going to have binary string. There we go. And then we are going to say full binary string plus equals the binary string. Bam. And then instead of printing our decrypted message, what we need to do is actually grab that save data function, or save file function again from our file metadata. So here it is. Let's just copy this, go back into our audio steg and go out of our class. So we'll just put it here at the top, why not? And now we have save file. So if we scroll down back to our decrypt file function, the last thing we need to do for this is type in save file with the output path, or output file equal to the output file given, and then the binary string is going to be equal to our full binary string. And now, if we go to our steg program and we scroll down to our decrypt, we're going to go to if it's audio, and we're going to say if hidden message, or if output file, sorry. So if somebody's trying to output the file, then we'll do this, else continue on with our message. So, or decrypting our message. So then we're going to say audio steganography.decrypt file, and we're going to pass in the input file as input file and the output file as output file. And let's see if we decrypt our function that we get, what we want. So let's do -d, and then our type is going to be audio, and then our input file is going to be output.wave, and then our output file is actually going to be, we'll just name it something.pdf, and we'll see if we get our PDF back. So when we press enter, it works, and then we actually get something.pdf back. Look at that. Boring data and something.pdf, they are the same, and we actually were able to encrypt boring.pdf into output.wave. That's awesome, and thank you guys so much for making it to the end of this course. Please give it a good rating if you found it useful, and yeah, thank you so much. And I will be creating another course for more advanced steganographic techniques, and then after that course, I'm going to be creating another course on how to use statistical analysis to actually detect if steganography has occurred inside of files. So those courses might be a bit longer and have a lot more content in them. But if you really enjoyed this, share it with your friends. And thank you again so much for watching.